BKW Physics, I'm Mr. McConnelly, and today we're going to start projectiles. And up on the board I've jotted down two very basic definitions of projectile and trajectory. So projectile is the thing that is launched through the air, and trajectory is the path of that projectile. And we're going to spend a lot more time later on discussing the differences in path or trajectory, but today we're starting very basic. And what we're going to start with here is things that are thrown, launched, and shot horizontally. So this lesson here is going to be on horizontal. In other words, if, the most common example, a person throws an object off a cliff. And when they throw the object off a cliff, they don't throw it upward, they throw it flat. And as it falls in this shape right here, which you'll recognize to be a parabolic or exponential shape. So the key is, though, that it starts horizontal right there. That's the key of this type of problem. That's what separates it from the other example we'll do later. So if we want to know how far it traveled, another way to say that is the range. If we want to know the range of what it traveled or how far it traveled, we're going to go back to a very basic first equation in physics, which is that average velocity is distance divided by time. So if you want to know how far, you're going to say the distance is the average velocity times time. And I've cautioned you, I've asked you repeatedly, be careful using this equation. Most of the time you can't use this equation. And what was the reason that I said you couldn't use this equation?
It's the average velocity.
Yeah, and average velocity means that you're not accelerating, right? You're going one constant speed. Now how if I'm throwing something am I not accelerating? Here's the thing. Okay, these problems have to be broken into what's happening horizontally and what's happening vertically. If you're talking about how far, you're talking about horizontally, and what's true about your velocity, your speed of the object horizontally. Well, let me explain. If I walk along here, and I throw this marker up in the air, and it comes back down, it lands in my hand, and I can do it without even looking. I mean, it's going to, I probably won't catch it, but it's going to basically come down right back to my hand, and if I get lucky, I can actually catch it. Now, here's the thing. That means that once I let go of the projectile, what's true about its speed horizontally? It stays the same. That's why you can use the equation. Because this velocity, which I'm going to now label with an H, stays the same. That's why I can use this equation, okay? And what I'm also going to add is that this distance is horizontal. So from now on, this is not a new equation. It's still the first equation in your reference table. But when we use it with projectiles, to remind ourselves, we're going to put the little H's there. So if you wanted to know how far the thing went, you just take how fast it was going when you let go, and you're going to time it by, or you're going to multiply it by how much time it was in the air. That's kind of our new equation, but it's not a new equation, it's the same old equation. Now, in the other direction, like if you want to know how high is the cliff, that's an up and down problem. So are we going to be able to use this equation if it's an up and down problem? Most definitely no. Because up and down problems, we always got acceleration and gravity. So you can't use a basic equation like this. But what you can use is one that you're very familiar with at this point. The distance is equal to the initial velocity times the time plus 1/2 gravity times time squared. You remember that equation. The only thing I'm going to add to it, I'm going to change, I'm going to tweak a little bit, is I'm going to be a little bit more specific for this chapter. For this chapter, if I'm saying how high, I'm talking about vertical, I'm going to put a little V next to the distance. I'm going to put a little v next to the velocity, and time and gravity, you know what those are. That doesn't change, okay? Now the reason I do that is because I'm trying to remind myself that the velocity I'm talking about is in the vertical direction. The distance I'm talking about is in the vertical direction. But let me make one more change here. Initially, right here, velocity initial in the vertical direction, how fast is the object going up and down when you release it? When you throw it horizontally, how fast is it going up and down?
0.
0. Everyone kind of sees that. So what happens to this term? 0, gone. So our equation actually is going to be just 1/2 gt squared. Now, let's apply this to an example like with some real numbers. I'll leave that up on the board for a minute. Let's say that my student Joe over here, takes my lunch. Okay? And I don't know why I did that, but I get very mad about it. And I go back over and I pull the lunch away from him, and I'm all crazy, and I throw the lunch out the window. And I made this situation up, can you tell? Okay, but I get just totally crazy and I throw the thing out the window. And when I throw the lunch out the window, that's all I can think of. When I throw the lunch out of the window, I throw it at a speed of 20 meters per second. And when I do this, my other helpful student in the corner, she has a stopwatch and she takes the time of how long it takes the lunch to hit the parking lot out there. Because we're in physics and we do stuff like that. So you time it and you realize that it took a time of 3 seconds to hit the ground. Okay? I don't know why you thought to do that, but it was a good thought. So, the first thing I'm going to do here in this situation is I want to know how far did the lunch fall every second? Okay, how far did it fall? How far did it fall? That's that. So I'm going to say this. I'm going to say, okay, dV is 1/2 gt squared. So, 1/2, 9.8 meters per second squared, that's negative. And the time, well, after 1 second, you do this math out on your calculator, and 1/2 of 9.8, you get about 4.9 negative. It's going down. And that's how far it fell after 1 second. So this is after 1 second. You repeat the process, and we'll kind of speed it up for the video purposes. After 2 seconds, the distance that it fell would be 19.6. After 3 seconds, the distance would be 44.1 meters. Okay? So we have ourselves some collected data here based on what I told you. Well, I also want to know how far did it go outward? How far did it go outward? So that's the range, that's this. So you say, okay, how far did it go? Would be how fast it left, 20, times the time, 1 second. So after 1 second, how far did you go? 20 meters, right? So this is after 1 second. After 2 seconds, can you do this in your head? 40. And after 3 seconds, how far did you go? 60. Alright, so what you've collected here, some information you've collected, and I kept the numbers pretty easy on purpose, is that over the 3 seconds it's going to go 60 meters out the window, and it's going to go 44 meters down, which by the way means that we're on a really tall building right now, which is not true because we're in school and we're all only in the 2nd story. But if we were in a really tall building and I threw it that hard and it took that long to hit the parking lot, it would mean that we were really high in the air. 44 meters is pretty high in the air. Okay, anyway, so the example is not that realistic, but that doesn't make a difference. You collected the data here. What I want to do with it real quick is I want to make a little graph for you. And this is going to be a hand-drawn sketch type of graph. What I'm going to have the distance vertical here and the distance horizontal here. And this is going to be 0 right there. So I'm going to do it something like this. In the horizontal direction, I'm going to make it 20, 40, 60. And I don't like this. Let me change it. Because I use negatives. Let me just do it this way. I'm going to move my axis up. I'm going to make this distance vertical, this distance horizontal. But I moved it up so that the zeros here and that the negatives can all go down here. That'll make it match our data better. So again, 20, 40, 60. And then our numbers go 10, 20, 30, 40, 50. Negative 10, negative 20, negative 30, negative 40, and negative 50. So as we plot these, after 1 second, I'm at 20 meters forward. And how far am I down? I'm about 5. So I'm somewhere in this range right here. After 2 seconds, I'm at 40 meters. And 40 meters corresponds to about a negative 20. After 3 seconds, I'm at 60 meters. And 60 meters corresponds to negative 44. So what I've got, what I'm creating here, when I graph it, is a picture of the actual path of the projectile. This is called its trajectory. So when I threw it out the window, its trajectory would look exactly like this. So that's it for today, physics.